new direction of the project that we are doing on symmetry, but now to have more application type of project. So we're considering also online monitoring, but using also reachability, but using symmetry to accelerate the reachability safety checking thing. This is in collaboration with Chao and Hebron and Cheyenne. Uh, so I actually stole these pictures from you, Ritika and Chao. And these are other applications where like we have fixed wing drones, fixed wing aircrafts passing through different paths and avoiding obstacles. So basically we want to do online monitoring, and the application would be done using, like the simulation would be written using Gazebo, safety checking would be done using, or reachability analysis would be done using DriveVR, and we're gonna use symmetry to accelerate the reachability computation. This is a gazebo model of the ECE building that we might use actually. The drones would be flying around between different rooms. The animations are not that good. So for the, in GEM, as the autonomous car that we are building with Katie's group, we did some version of online monitoring where every time we get a state update, we compute a reach tube for the next 5 seconds and then check intersection of that reach tube with the expected path of a pedestrian passing through in front of the car. And if the reach tube of the car intersected with the pedestrian, then we say it's unsafe, we brake or decelerate. The problem is it's expensive to compute the reach tube every time, especially if we want an online performance. Uh, and luckily, under certain conditions on the dynamics and the path that is the car or the drone passing through, then we might reuse some of the reach tubes. We can just cache whatever we have, whatever whenever we compute a reach tube, and then reuse it again whenever applicable. And here we are showing in the, I can show the figures where these are the paths that the three drones in the previous slide were passing through. And on the right, I'm showing these simulations in some unified coordinates. So in these unified coordinates, the drone is always like is always going to the origin. So always the waypoint is the origin, and we are changing the initial state accordingly. So this simulation here would be this simulation here. The blue simulation here would be the simulation here. And the intuition behind this is this will increase the reuse of the simulation in this case. And in the bottom, it increases the reuse of the reach tubes. So if there is a drone, here we have a single agent passing through this snowflake path, then every time, and then we have translation type of symmetry. These are the conditions on the dynamics. I will not discuss them now, but assume that we can use the reach tubes if they are translation invariant. So this edge, this edge, this edge, the dynamics would be similar. So we can just copy paste reach tubes. And here are the unique reach tubes that we computed for different unique waypoints. And the intuition, like the motivation behind this is that transforming reach tubes, transforming simulations is cheap. However, computing them from scratch entails integration, complicated ODE in the case of a simulation, and in the case of computing reach tube, it would be optimization problems, integration, multiple expensive operations. And that would hinder online performance, while transforming whenever applicable would be a good direction to pursue to try to get an online performance. And this project is about implementing this idea in Gazebo. And first we are gonna use the Hector model that it's being already used in Sci-Fi House and Chord. We know the dynamics of this, but they are complicated dynamics. So instead, we will use another simpler model. It's also a 3D model, but it abstracts all the mechanical and electrical components of the Hector model to compute the rich tubes. So remember, to compute rich tubes, we need dynamics. So instead of using the dynamics of the Hector model, we're gonna use the dynamics of an abstracted drone that is only 9-dimensional. And we're gonna use a waypoint tracking controller to, it's a PID controller, it's already part of the model. And later we're gonna use Chord to share rich tubes between drones. So remember that symmetry would help us share and reuse rich tubes. And to share and reuse, we need a cache. And that cache would be a shared variable between the different agents in the Chord program. And we're gonna use the Sci-Fi House Gazebo-based simulation environment to actually simulate the whole thing. And we might have different drones, uh, multiple drones passing through different waypoints or accomplishing common tasks that they can share. Uh, but we will use Chord to implement the cache as a shared variable, and also to share the actual reach tubes of the different agents to actually check collisions. So when there is a collision, then we might need also to re-implement or redirect the plan in a way that is safe. So this is just a summary of what I just said. We have a safety block that takes as input the current state estimates of the different drones and how how much we want to look ahead, and the requirements. Basically, the requirements would be just collision avoidance for now. And the output would be rich tubes. These rich tubes either computed from scratch or reused from the shared cache, and a safety indicator saying that these rich tubes are intersecting or not. Uh, Everything else I already talked about. Here's the gazebo environment of the ECE building, and we can see here the two drones, very small two drones. We have several research questions to answer. What are the computational bottlenecks? Should we do the computation of reach tubes in the individual drones or in the individual drones computers, or should we do that in a centralized computer? That's the edge versus cloud partitioning of computation. What are the computational bottlenecks, how to use. So far I only talked about the symmetry of the dynamics, but we also are considering, or we will tackle the point of symmetry of planar. Symmetry of the planar, that means that sometimes you can adjust the plan so that you only use, or you only go to waypoints that you have the reach tubes for, to avoid computing reach tubes from scratch. So like, see what's in the cache, see what are the possible waypoints that you can go to from the current waypoint, and so that you don't, if you don't have budget in time, and whenever you are free and you have more time to compute, then you compute more reach tubes and save them in the cache. And what else? So far, we are also considering the case where the agents do not interact with each other. That means they don't check each other's state and then adjust the plan. They are only checking safety. So individually checking safety and then adjust their own plan, but they are not communicating with each other to reach a consensus. That's it, basically.